waste-to-energy plants are powerful tools in our quest for sustainable energy. But what about the stuff coming out of their stacks? Emissions are a central concern, and understanding how they're formed, controlled, and their real environmental impact is crucial for any city aiming for both clean energy and a sustainable future. The journey to understanding starts right inside the plant, where chemistry, engineering, and cutting-edge technology all come together. So, what exactly are we talking about when we say emissions? From a waste-to-energy plant, there's a mix of substances. First, there's carbon dioxide, or CO, which comes from burning organic materials. Then we have nitrogen oxides, NOx for short, which form under the high temperatures inside the combustion chamber. Sulfur dioxide, or SO, is another one, and it originates from sulfur found in certain types of waste. We also have particulates, which are basically fine ash and dust. And finally, there are tiny but potent compounds called dioxins and furans. Each of these has different health and environmental implications, and modern plants are designed to tackle every single one. To control these emissions, you first have to know where they come from. The CO is a natural byproduct of burning organic waste like food scraps, paper, and yard trimmings. The NOx forms when nitrogen, which is abundant in the air we breathe, reacts at temperatures above 1,200 degrees Celsius. So is primarily linked to things like plastics, old textiles, and rubber in our municipal trash. The most infamous ones, dioxins and furans, are trace compounds that can form when materials containing chlorine, like some plastics, don't burn completely. Knowing the why and wherefore each emission is the key to designing systems that can effectively neutralize them. And that brings us to the really cool part, the technology. Modern waste-to-energy plants use a multi-layered defense system to clean their exhaust gases. First up, we have scrubbers. Think of these as giant washing machines for flue gas. They use an alkaline solution to neutralize acidic gases like sulfur dioxide. Next, to catch all the fine particulate matter, plants use something called baghouse filters. Imagine a massive, high-tech vacuum cleaner with incredibly fine filter bags that trap even the tiniest particles. For the nitrogen oxides, we use a process called selective catalytic reduction, or SCR. This system uses a catalyst to convert harmful NOx into simple, harmless nitrogen and water. And for those tricky dioxins, furans, and heavy metals, activated carbon is injected into the gas stream, which acts like a magnet, pulling these pollutants out together. These technologies ensure that what comes out of the stack meets the strictest international environmental standards, making today's plants a world away from older incinerators. Of course, you can't just install this tech and hope for the best. Constant monitoring and strict regulation are non-negotiable. That's where continuous emissions monitoring systems, or CEMS, come in. These systems are mounted right on the stacks and track gases second by second. Environmental authorities require this data to be reported in real time to ensure the plant is always operating within safe limits for CO NOx, so particulates and dioxins. Regulations, like the EU's Waste Incineration Directive and standards from the US EPA, set the permissible limits, guaranteeing that these facilities protect both public health and the environment. Now, to get the full picture, we need to look beyond just the smokestack. A life cycle assessment is essential. Yes, waste-to-energy plants emit CO, but they also prevent the release of methane from landfills. And methane is a greenhouse gas that's 28 times more potent than CO over a 100-year period. On top of that, these plants recover valuable metals from the ash for recycling, and the remaining ash can often be used in construction materials like roads and concrete blocks. When you add all these benefits together, avoided landfill emissions, energy production, and material recovery, waste to energy often results in a net environmental benefit compared to just burying our trash. And the story doesn't end there. The field is constantly evolving. Researchers are developing advanced catalysts that can virtually eliminate the formation of dioxins. Artificial intelligence is being used to optimize the combustion process in real time, fine-tuning temperature, oxygen flow, and the mix of waste to minimize emissions from the get-go. There are even pilot projects looking into integrating carbon capture and storage technology with urban waste-to-energy plants. All this innovation is making sure that waste-to-energy will continue to be a sustainable, low-impact energy source for our future cities. This isn't just theory, it's happening right now all over the world. In Copenhagen, their famous Copenhill plant uses multi-stage filtering to achieve near-zero emissions, and it's so clean there's a ski slope on its roof. But in Osaka, Japan, they combine advanced gasification with SCR systems and AI-powered monitoring for maximum efficiency and cleanliness. And in Vancouver, Canada, their facility is a model for integrating emission offsets and creating a circular economy by recovering and reusing ash. These cities show what's possible when technology, smart regulation, and a commitment to sustainability come together. In the end, effective emission management is what transforms waste-to-energy from a controversial idea into a cornerstone of sustainable urban living, with advanced technology and rigorous, transparent monitoring. Every ton of waste we can't recycle can become a source of clean energy without compromising the air we breathe. It's a powerful step toward a cleaner, greener future. Thanks so much for watching. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe for more insights into sustainable technology. We'll see you in the next one.